Okay, so in the last video I talked about a definition for an acid and base using the Bronsted-Lowry definition, and we adjusted our idea to think of acids as proton donators. So if I have something like HNO3 and we view it as reacting with water, then we see that it donates its proton to the water to form H3O+, which we call hydronium. And the remaining anion can remain dissolved in solution. So that's a donator. And bases, as proton acceptors, where the proton then goes from the water to the base, making NH4 or ammonium and hydroxide. So that's how an acid is a proton donator and a base is a proton acceptor. Water then is a tricky substance when trying to define it as an acid or a base. Usually people would say it's neither, but it's a little bit more complex than that. Water is something that we call amphiprotic, which means that it can act as either an acid or a base depending on the situation. Water, for example, will react with itself to produce hydronium and hydroxide. In this case, this water is acting as a base where it accepts a hydrogen and becomes hydronium, but it created this hydroxide. Alternatively, this water, who donated its proton, is acting as an acid. So it can react with itself to be an acid and a base to make both hydronium and hydroxide. This is called the auto-ionization of water. And it doesn't happen very often. It happens such that the concentration of hydroxide or hydronium in water naturally occurring with no other acid or base species is 1 in 10 to the 7 or 1 in 10 billion. So you can see this is very unlikely, but it does happen from time to time. And so water can act as an acid or a base when there's nothing else around, creating a naturally occurring population of hydroxide and hydronium. It's not the only amphiprotic object or amphiprotic thing. If we imagine baking soda, NaHCO3, then that would dissociate to dissolve into solution as Na plus and HCO3 minus. So this is baking soda, sodium bicarbonate. It's breaking down into sodium and bicarbonate. And really, we're not too interested in the sodium. He's not interesting. It's the bicarbonate. Bicarbonate can also be amphiprotic because it can react, for example, with an acid. And if it did, it would act as a base. So that hydrogen that could have gone to a water to make hydronium instead might go to the bicarbonate to make carbonic acid, and then the Cl minus would be the resulting anion left over. And so here, bicarbonate is acting as a base, accepting hydrogens from that acid. Alternatively, so that's how it acts. That's how baking soda acts as a base. If baking soda was in a solution with a lot of base, something like sodium hydroxide, then we could imagine that this bicarbonate could act as an acid, donating its proton to the NaOH, and it would form NaCO3 minus and H2O. And so here it donated its proton to the hydroxide, creating water. So here it acted as the base, accepting the proton, and here it acted as the acid, donating the proton. Clearly, these reactions can get a little complicated, and they're very dependent on the situation that this is in. Sodium bicarbonate would behave normally as a base in neutral water, but it can behave as an acid or a base depending on the situation. When we have these more complex reactions that can go both forwards and backwards, we have special names for the products associated with them. The acid produces a conjugate base, and a base produces a conjugate acid. So for example, if we imagine the reaction between ammonia and water to produce ammonium and hydroxide. Here, in this side, if this reaction is going forward, ammonia is acting as the base, accepting the proton from the water, and the water is acting as the acid, as it is a proton donator. Now on this side, these two products get produced, but this reaction can go backwards. Instead of, I could just write it like that, but I'm going to do this. Let's just imagine that this reaction went backwards to produce NH3 and H2O. Now, this NH4 plus has donated its extra proton back to the water to reproduce ammonium and water. Here, what was the base is now acting as the conjugate acid. We use the word conjugate because it's the reverse reaction. And here, what was the water or the acid is now acting as a conjugate base. So if we imagine a forward reaction, we have a base and an acid, and then if we have the reaction go backwards, so instead of one guy donating his proton to the other guy, now they're reversed in roles. Whoever was the base now becomes the acid, and whoever was the acid now becomes the base. The giver becomes the acceptor, and the acceptor becomes the giver. We call it conjugate because it's referring to the reverse reaction. Strong acids, like HCl, have acid-base reactions that occur basically only in one direction. All of that acid works to donate its protons and react in this direction. So if it's strong, it all goes this way. Weak acids and bases have competitive forward and reverse reactions. If I take something like H2CO3 and I put it in water, it can become H3O plus and HCO3 minus, but it doesn't totally like to live like this. It will also go backwards. We call that a weak acid, and usually it either happens a whole lot or it's a really competitive process and the two reactions sort of balance each other out. These guys obviously have much more extreme acid/base properties, like pH. And these guys are obviously a lot more complicated and often can do things like be amphiprotic and all kinds of other stuff like that. The reactions can happen differently in different conditions depending on what the temperature is or what other materials are in the water, or a variety of other things like that. So those are some more definitions and a little bit more discussion of acids and bases considering the Bronsted and Lowry reactions for acids and bases.